Hey, CHEM345. I wanted to pop in and answer some of the questions that I've seen on Piazza, as well as some of the questions I've been getting during my office hours, and some I've seen during the large group Q&A session. So as you can see, we have something going on Monday through Thursday, 11:45 to 1 p.m., whether that's large group question and answer or the office hours with me. You also have your discussion that takes place twice a week. Also, you've probably noticed that CHEM345 is very different than CHEM343, especially in the beginning. We've learned 4 techniques. I'm going to walk through a little bit what you need to be able to recognize. I'm also going to walk through, in a separate video after this, I'm going to walk through 2 examples of how you can take a molecular formula, your IR, your mass spec, your proton NMR, your carbon NMR, and how you can determine what the structure is. The way that I do it is slightly different than the lecture videos that you've seen so far, and so I thought it would be useful, because we all learn differently, to walk through it with me, and I'll show you how I'm thinking about it rather than you just seeing an answer written down. And I also think that compared to the lecture videos, the way that I explain some things will be different, and it might be very helpful. So what I want to do is I'm going to walk you through just kind of some of the basics, some of the questions that I've been seeing. Then we're going to dive into 2 specific questions. We're going to walk through exactly how to do them. Of course, someone asked for me to include some things about splitting and all that stuff. We will absolutely get there, and I will explain some of those things as well. From these spectra, you can determine whatever compound you have. We will soon in 345, we will be getting into new reactions. We will be getting into mechanisms and all of that stuff. Some of the mechanisms you have looked at are for mass spec. This is 70 electron volts being just demolishing these compounds in mass spec, okay? I'm also going to show you there is an error on the appendix. I'm going to show you actually the correct appendix. I've just uploaded it. You should also now have access to your discussion. You should have access to the answer keys for the discussions this week. Okay. You should also see the problem sets, and you should also have an additional problem set with lots of these unknown compounds with 4 spectra. That's going to be very reminiscent of what you're going to see on Monday for your quiz. You have a quiz on Monday. If you're just learning about this now, where have you been? It's listed under the assignments. You have a quiz Monday. Let me just talk real quick about the quiz. So the quiz will be in similar format as everything else you're going to be submitting here in class, as well as the exams. What you're going to do, you have 3 ways to do this. You do not need a printer. You do not need a scanner. You do not need a tablet. As you guys know, in my large group question stuff, I've fought with this a little bit. I think I've figured it out now. Okay, here's what you're going to do. On Monday, the quiz will open up at 7 a.m. I think it's 7 or 6 a.m.? 7 a.m. You're going to have 24 hours to do this. The quiz will not take that long. Once you open it up, it will still be available for 24 hours. Okay, I have not sectioned off the time for that. So you can open it up, look at it, and then something happens and go do the thing and then come back, okay? I did this for 24 hours because I know some of you are working. Because of the pandemic, there were months where people couldn't work. I understand that. So I'm just trying to be as flexible as possible. Once you open the quiz, you have 24 hours to take it. Well, wait, 24 hours from 7 a.m. Mondays. So 7 a.m. Monday to 7 a.m. Tuesday. Don't wake up at 5 in the morning on Tuesday and try to do it. Just try to find time on Monday, okay? You can use your friends, you can use your colleagues to do this. You cannot use your TAs, and you cannot use me, okay? You cannot use other professors. Do not use your tutor. If you have a tutor, do not use them either. And I'll have that listed on the quiz. So how to take the quiz? 3 ways. You can either download, you can pull up the quiz on your Canvas page, okay? Number 1, you could print it off, right? Print it off. You take your piece of paper. This isn't a piece of paper. This is a newspaper. Take your piece of paper, and you can write the answers on it. There will be at least 2 pages, okay? Then what you can do is you can take, I hope everyone has a phone. You can take a picture of it. You could scan it if you have a scanner. Take a picture of it, change it into a PDF, okay? And then you're going to submit it as one document. For all 3 of these methods, if you do not have a scanner, I do have a scanner. Anyway, I wouldn't use a scanner. I would just use my phone. I'll put it right here, the Genius Scan is a free app that you can get for your phone. You can take a picture and it turns it right into a PDF, and then it also can take multiple pictures and combine it into one PDF. The order has to be the same, otherwise you get a 0. Yeah, that's right. Part of why I do this is just so that it's you actually get graded. Otherwise, if you do it wrong, we can't grade your assignment, and then there's no way for us to recover it. So that's the first way. Download it, print it off, take it on the piece of paper. Okay, you don't have a printer, no problem. Pull it up on your computer, use a separate piece of paper, and as you're looking on it, you're gonna write number 1, and then you're gonna write your work down on it, okay? The third way to do it, again, after you write your work down, take a photo and then send it a PDF. The third way to do it is if you do have a tablet, you can download it on your tablet, make the notes you need to, save it as a PDF, and upload that. I will write the quiz so that it will be somewhat easy. It's hard with Spectra, but I will make it somewhat easy to where you will be able to kind of draw what you're thinking without having that piece of paper printed out. And you'll see that as I go through examples. Quiz on Monday, you have 24 hours, there is no time limit. On the top of the quiz, I will tell you about how long the quiz should take you, okay? I haven't written it yet, I'm writing it tonight. I don't know, probably 35 to 40 minutes is what I'm thinking, okay? So if you, wherever that time is, if it takes you much longer than that to finish the quiz, you know you need to study a little harder. So that way you can have time on your exam to get through the entire exam, okay? If you do it really fast, you might just want to check your work to make sure that you got it right, okay? Again, you can use your colleagues for this, but you cannot use a tutor, you cannot use professor, you cannot use your TAs. You can use the internet. You are welcome to use the internet. Good luck. So that will be Monday. And then again, we have the lecture videos that I need you to be keeping up on. And so anyway, this is the first of many videos I'll be doing through the course. What I want to do is dive into my tablet. So let's do this. Okay, let's jump into your appendix here, and this is what you're going to be using for your quizzes and exams. Let's just jump to an error. Oh, I already have it drawn. Whoops. I already have it drawn out for you. This is on the page, what is this, page 11 or something? This is for the Mass Spec. I've already updated the appendix that you have now online, so you can see it correct there. Essentially, I'm just going to draw this in red. Again, this is actually a radical in order for this to do this H-atom transfer and then loss of water. Or in this case, it's showing it could be an OR. So what I want to highlight though is that I will not be, let me redraw this for you. I already drew this for a student. So I will not be asking you to do weird H-atom transfers. They will make sense. They will make chemical sense. Page 597 in your book, 12.6C has exactly what I'm talking about. Essentially, in order to do an H-atom transfer, I would only want you to know that it needs to be able to conform to a 6-membered ring transition state. And I will show that with an example. So if you have, say, this alcohol, 1, 2, 3, 4, 5, cool. What can happen is one of the protons here can be poised into this 6-membered ring. Let's just pretend we already shot this with 70 eV to kick out an electron, okay? And so now what's going to happen, and maybe this is easier if I draw the arrows in blue, is you're going to end up getting this H-atom transfer. Here, okay? You can actually lose water. Oh, I should use blue again. Whoop. Cool. And then here you're going to have this 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Notice how I'm always counting my carbons. It's really easy to forget, to lose where you're at. Always count them. So This is essentially all I would be testing you on. I wouldn't be asking you to do an H-atom transfer here unless it's in a 6-membered ring transition state. So just know that for quizzes and such in the future. What I want to do though is I want to jump through the 4 different types of spectra that you have been looking at. This is the bonus problem set with more spectroscopy and spectrometry. Essentially what you're doing is you're given a molecular formula, and you are asked to draw what that molecular formula is. The first step in this is going to be to figure out how many double bonds this has, and we'll walk through that. Before we get there, I just want to give a couple little pieces of advice about these 4 types of spectra. For mass spec, I will always put the corresponding m over z. If you're confused about what m over z is, all it is the mass over the charge. I will only be asking you, I guess, when the charge is going to be +1. It's always going to be +1, okay? We won't get into anything that's too crazy here. Same thing with the H-atom transfer. We won't do anything crazy there. So mass over charge. So anything that you see in this detector, this is relative intensity. This means that 128 is the most intense mass over charge, m over z, that is observed when this compound is just obliterated with 70 electron volts. That means it's 100. It's just relative though, okay? So that means it's something like this peak, or I don't know. This peak might be able to determine, but these I will not ask you. But if I wanted you to give me an answer for this one as far as the fragmentation, I will write the number on top of that. Just know that, okay? So I want to go next to IR. What is IR good for? IR is so good for functional groups, okay? I've actually used IR in my grad studies, which most organic graduate students do not use IR. It is actually really helpful when you are just trying to make sure that you have a functional group that you're looking for. What kind of functional groups is it really good for? This would be useful to kind of just pop back over to the appendix briefly. The frequencies of various stretches and bends. Don't get too concerned with whether or not it's a stretch or a bend. I'm more concerned with you knowing the practicality of this technique in regards to new reactions and mechanisms and such. So really what I want to highlight is probably one of the most important ones is this carbonyl stretch that you are going to see here. For aldehyde, ketone, carboxylic acid, do you see how this changes? This is really important. On the IRs that you are given, you will have that number. You will have the frequency of what it is. On some of the ones in these examples, you don't, but you don't really need them, but I will include it. Another thing that's really helpful on an IR is if you have an OH peak. We already know that these are broad, and these come around 3,400 here. So, for example, if you had a carboxylic acid, you would know that you would have both of these. These are very important. There's something with the IR, though, I want to bring up. I've seen this question quite a bit. For IR, around 1,500 and lower, this is considered the fingerprint region. And as the name suggests, the fingerprint region is very specific to every compound. I will not expect you to be able to pull out certain frequencies in here and relate them to functional groups. The majority of them will take place above 1,500, okay? And again, one thing I will try to do, I will either tell you important frequencies, because it's kind of hard to see on this. So typically I will give you a list, which will include frequencies as well as the transmittance. Just so you know, transmittance, if you look at this, it's 100 down to 0. So something that is a strong signal will be at a lower transmittance number. So just a little heads up there. It'll help you determine what's on that list. Okay, let's move to NMR. What's NMR good for? Whoa, where am I at? Here we go. What's NMR good for? NMR is so good for everything. It is fantastic. What you're going to find as you start to figure out, you have your molecular formula here. You figure out the number of double bonds. You might then find yourself jumping to the IR immediately to see if maybe there's a carbonyl. You might have to just jump right over to the proton NMR. How you solve each problem is going to be different based on what you're kind of starting to think might be in the compound, okay? NMR, there's a couple things I want to go over. Oh my, where's your x-axis? Okay, so it should always be, so it's ppm, this is TMS, this is just what we calibrate the NMR to, so we're not going to worry about that peak. I will either have them listed like this, or I will have them zoomed in so you can see it very, very clearly where everything's happening. There's a couple things I want you to see. You see this blue line here? What is this thing? This is showing the integration over this peak, okay? So essentially how much area is underneath that peak. And the integrations here are all relative to each other. So you might see, well, I'll get into that. In this case, they're all 1H, okay? How did I find that? It's listed here. These are all 1H. You might have an example though, and I'm just going to highlight this real quick. You might have an example, this is theoretical, if you have something, say, that's 1 to 2 to 1 to 1 to 1, okay? But let's say your chemical formula says that you don't have, what is this, 3, 4, 5, 6 hydrogens. Let's say your chemical formula has 12 hydrogens, but the integration says 1 to 2 to 1 to 1. What the hell are you supposed to do? Multiply by 2. Typically, these integrations are just given as ratios, unless you know that one of the peaks is specifically 2 hydrogens or something. A lot of times we would just integrate, get a ratio, and then look at what our reaction was. In this case, if your formula did have 12 hydrogens, you'd multiply everything by 2. So then it would be like this. Again, this is theoretical. This is not talking about this specific spectra. Just know that the molecular formula and the number of protons should add up. Here's another thing. I've been getting questions about how are you supposed to know what type of protons these are. I want you to keep this in mind. Anytime you see something around 7, this is most likely, and some of you may already know, this is most likely aromatic. In fact, the majority of the time it will be aromatic. How do I know that? I'm going to use my appendix. I'm going to go to the first page of the appendix, and I'm going to look to see where a CH bond on an aromatic ring is. Here we go. We're right here, and we are around 7 ppm, okay? Now, where this takes place in this range is going to be dependent upon what is bound to the benzene ring. In my office hours today, I went to town on benzene rings and electron withdrawing groups and electron donating groups. And unfortunately, my audio, something happened to it, so I just have the written form, so I need to go back through and edit that. I might make a separate video. But this is dependent, all of these ranges are dependent upon what is this R, what is bound to this R. Something to keep in mind with NMR. There are 2 ways that this can be shifted, right? You can be shifted to the left. This would be considered downfield. And this would be de-shielded. What does de-shielded mean? This means it has a less electron density around it. Think about electron density as a shield for the compound when you put this compound into this magnetic field, okay? The other way would be upfield or shielded. What the heck does this mean? Why do you need to know it? So, in this case, let's look at a quick example. If I have an alkyl group that is saturated, it's going to be lower ppm than if I have an alkyl group with an X, say a chlorine or a bromine. We know those are electronegative atoms. See how the shift, it shifted, where did it shift? It shifted downfield. When you add electron withdrawing groups, you tend to shift it downfield. And when you add electron donating groups, you shift it upfield, okay? These are important concepts to know. That means even within the range of an aromatic ring, you can determine which of the CHs are where based on the electronics of that ring. And I will try to find, now that I'm looking at it, I'll try to find an example for that for you guys. All right, let's just do one more quick thing. There's a couple things I want to go over with the carbon NMR, just generic. carbon NMR here. How do I even know it's a carbon NMR? This is kind of funny. There's no, it doesn't even say carbon NMR, right? How do I even know? Look at this. The range is 0 to 200. That's typically the range for carbon NMR. You'll also see that there's no splitting. Oh, I just got this fly. I've been trying to kill this fly for an hour now. Okay. You'll see that there's no splitting either in this case. Again, TMS. With carbon NMR, what I want you to see again is that there's certain ranges for things. Does anyone know what this is? This is solvent, actually. How do I know that? I know that because I have done too many NMRs in my lifetime. You'll see that solvent quite a bit. Let's find it on here. Can you find that solvent here? The way you would look is you would look at carbon NMR, right? Do you guys see that 77? Right here, chloroform. That's right. For NMR, we use deuterated solvents. And the reason we do is because deuterium is picked up in a different frequency range than protons. And so it allows us to see the protons. If we were to use CHCl3, that would really make it difficult for us to see our compound. But in this case, we do have a carbon, and there is a, 1.1% abundance of C13, and C13 is really what we're picking up in the carbon NMR. That's also why we have to have close to 25 to 50 milligrams of it. We need more of it than, say, a proton NMR. Okay, so if you see some peaks that you're not really sure where they're at, they're likely solvent that has been used. If it's something weird, I will tell you what solvent is. If it's not chloroform, chloroform is very common and the majority of them will be chloroform. But if it's something wonky, I will definitely let you know. Okay, let's go back here. Now, we just kind of walked through a little bit of each of these, but what I want to do is I want to show you the thought process on how you can use all 4 of these. There is not one size fits all for all of these compounds, okay? You will find that you will jump between them, and that is really important, and I definitely want you to feel comfortable doing that. Let's see, what do we want to do?